Hi, everybody, and welcome back for Logistic Regression. So, Logistic Regression is really about predicting the probability or the odds that something is going to fall into one of two categories along a dichotomous outcome variable. You have binary logistic regression, which is just two numbers, and then you have multinomial logistic regression, which is two categories of dependent variables. Your dependent variable should be dichotomous, as I've mentioned. You can have one or more independent variables. They can be continuous or categorical. You need to have independence so that they are explaining their own portion of the variance of the odds. And there needs, of course, be a linear relationship. You need to test these first three assumptions before you test the fourth, because if any of these three don't exist, you can't even bother with the fourth. So, all right, so these are the instructions for how to do a logistic regression. So I've entered those in here for you. And then I've given you an example, an explanation, which is pretty solid and pretty good. And so let's go through a few of those things. So first thing you want to look at is, how much of the variance is explained by your dependent variable. So in this case, we're going to look at this. You're going to get a model summary. It's going to give you a Cox and Snell R-square. That one cannot ever achieve 1. So that's really not the preferred one. The Nagel-Kirk R-square is the one that we tend to use in the field because this one can actually achieve a 1, remembering that's a perfect correlation. So important to know, and what one is preference. Then we get a classification table. This is much like the one we just saw in discriminant analysis, where we're saying, okay, is this person going to have heart disease? Yes, no. And when we predict it, are we right? Are we wrong? So this is, you got the no's correct. Here we got a false negative. We thought it was going to be a negative, but it was a positive. So this is really where we talk about our sensitivity, right? Specificity, sorry, our specificity. And then we have our, so you have specificity and you have sensitivity. Sensitivity is where you correctly predicted by the model. So this is what the yeses, so the true positives, right? And so we have that information here. And then we go on down to variables and equation. This is where we're going to get our coefficients. Here are our coefficients. We want to see if they're significant. You can tell some of these are not significant. And then we also can look at, well, this is, I wanted to show you how this one's interpreted. So we have these right here, right? And so the way we're going to interpret it is logistic regression was performed to ascertain the effects of age, weight, gender, and oxygen on the likelihood, this is logistic regression terminology, on the likelihood that the participants have heart disease. The logistic regression was statistically significant for the chi-square 4 degrees of freedom for 27.402, p-value of less than 0.0005. Now, where did we get that information from? So we got our chi-square should be here. I don't see where we calculated the chi-square on this one. So usually you get a document that does show your chi-square. So you'll just have to trust me on that one. Chi-square, and then the model from the Nagel-Kirk R-square showed that 30% explained the variance in heart disease, and it correctly classified right here 71% of the cases, which is a pretty strong model. Males were 7.02 times more likely to exhibit heart disease than females, and increasing the age was associated with an increased likelihood of exhibiting heart disease, but increasing the oxygen was associated with a reduction in the likelihood. So this is a negative correlation. So that means that as we have more of this, then there's less chance of heart disease, right? This is gender, which is female, so we have to do the opposite of that for the male. Then we have our weight and we have our age. So all of those are explained there. And here's how we do, right here. This is how we say that yes is 7.027 times more than the male. So we calculated that. So I've explained all that here for you. Okay. So I'm trying to think. This is where the 7.027 came from, is this exponent coefficient right here. Okay. So I can say that the older you are, the chances of, or the likelihood of you getting heart disease is going to increase by 1.08. So as the age goes up, your chances for heart disease go up. As your weight goes up, then the likelihood is, being magnified. Here, not so much, right? Because it's a negative. So this is going to have a less impact, a likelihood on what's happening. Okay, hopefully that makes sense. Now let's look at this data source, which I want to give credit to my colleague at East Carolina for providing this resource. And then we will evaluate this one, and then we will go from there. All right, so I want to bring up their actual work. So this is the explanation that I've embedded in there. This professor did such a great job, I didn't need to really do it again. So I wanted to share the results, but I want to show you kind of how we get to this. All right, so here is our logistic regression. So this is the data set, which is embedded in there for you. And then we are going to run our logistic regression. So the way we're going to do that is we're going to go to Analyze, Regression. And we're going to go to, in this case, multinomial, because we have more than one. So in this situation, we want to know the dependent is going to be, oh, actually he ran it, oh, this is the binary. So this is the first one he ran. Let's run down to the second one so we can run everything together. Interesting, he's gonna do, all right, let's do it the way he did it. Okay, so we're gonna start up here. And the first thing we're gonna do is we're gonna actually run a bivariate. So we're going to do it across two. So we're going to go to regression. We're going to go to binary logistic, which is going to pop up and look like this, right? And then we are going to do what they tell us to do here. So we're going to put decision in the dependent and covariant in gender. So we're going to do decision in our dependent, which is what they decide to do. And then gender is going to go in the covariant. Enter is here, so I think we're good. So we're going to click OK. That's going to give us these results. Yep, looks like theirs, so that's good. So in this particular study, what was interesting is they had 315 students, and they had the students look at a research proposal. And then that research proposal, the researcher was going to be basically doing harm to cats. And so the students had to make a decision about whether they were going to stop the research or continue the research based off the researcher's explanation of why this harm to animals was necessitated, right? So it's talking about animal research. So there was lots of different things that they were doing. So there was a study that said that it was cosmetic. There was a study that was testing the theory of something. There was one that was testing synthetic meat. Another one was testing, I think, about a veterinarian disease. And so there was all these reasons why they could do different research, right? And so they were making a decision about start, stop, continue the research based off that. All right, so let's take a look at some of these results and walk through them. Okay, so the first thing we want to look at, and I'm actually going to make this bigger so we can see this. Oh, come back. There we go. Ooh, very big. All right, so the first thing we're going to do is make this just a little more. There we go. All right, so we have 315 cases. And then block 0 is the initial model. So the initial model is just looking at the intercept, right? And in this case, the decision to start and stop. So it's like all of them together and just saying, okay, start, stop, no independent variables accounted for. So 187, 128, and just in general, just the constant of just being present and making this decision, 59% were appropriately predicted. So that's without any of the independent variables. Okay. So in this particular case, we're also going to look at the variable of equation, which is similar to what we just looked at with discriminant. And our odds coefficient is negative 0.379. And over here, we can see that's significant, right? And what we're saying here is that our predicted odds, this exponent beta, is 0.684. And what that's saying is that our observed odds are 68.4%, right? So 68.4% is the chances that we observed it correct. Now, we're going to add block 1. And when we go to block 1, this is where we add the first step. We're trying to see, okay, now we add in some variables. How is that going to help our model? How is that going to help it be more accurate? We're going to again look at our Cox-Snell and our Nagel-Kirk. And here we can see this is a very good number, good to go. This is great, all right? Then we're going to create our odds statement, just like we did with the prediction equation and multiple regression and discriminant analysis. We're going to use the same process using our variables in our equation. So having gender now, we've added gender to our equation, right? That was our covariant. So now we can see that that's negative 0.847 plus 1.217. Now, gender is going to be a dummy variable, which means you're male or female in this particular study. And so if you're one gender, you're going to be, let's look and see which one it is. So we'll go, that's the wrong one. So in this one, let's look at gender. Let's look at variable view. We go to gender. So if you're a female, you would be coded as 0. If the participant was a male, it'd be coded as 1. And what that means is when we do the equation, if this person is a female, there's going to be a 0 here. So that means that this is going to be all that's left in that equation, right? If it's a male, we're going to have 1.27 stay in because it's going to be multiplied times 1. So just kind of understanding how the odds prediction works. And it's explained more here to help you understand how to do it. But basically, by looking at the odds that we have that this is going to happen, right, which we've calculated right here, the odds for a man. The man is 1.448 times more likely to decide to continue the research than decide to stop. For our women, we've got to do the convert odds to probability. So that left us with our model predicts 30% of the women will decide to continue the research. For our men, it's 0.59. So 30% will decide to continue. We've calculated that here with the 0.429, right? Remember that equation I gave you, which was negative 0.847 plus 1.127. That calculates this, and then when we know what our odds are, we get this, which tells us that women is only 0.429 is likely to decide to continue as she is to decide to stop. And then we do this odds equation, what's called convert odds to probabilities, to calculate the percent who will choose to continue the research. So 3 steps. So we look at this, we check this, then we can do this formula, which is our kind of prediction equation. Then we can calculate how many times more likely than the other group. And here we can calculate how many will choose to do the positive of what we're studying. Okay. So there's more explanation here. Let's go to the classification. Again, you've seen this already, but stop to stop, stop to continue. This is a false negative and this is a false positive. And so that explains, so false positive would be predicting that the event would occur when in fact it did not. And a false negative would be predicting the event did not occur when in fact it did. So again, remember specificity and looking at the different ways in which you can interpret your findings. So now we are going to go to SPSS. You're going to analyze descriptive crosstabs, and you're going to put these in here. And you're going to click on your stats and go to chi-square and observe counts and rows. So you can do that in SPSS. We're going to get our output, and it's going to show us exactly what we just calculated using the odds equation. It's going to give us the same findings. Remember how we did these cross tabulations for chi-square a couple of weeks ago? So this is going to match the information that we just calculated. So that's good. Way to go. All right, we'll also notice that our chi-square is getting smaller as we move closer to a more precise equation. Let's add in multiple predictors. So in this particular one, we're now going to add multiple predictors. We're going to have our decision still be our dependent, and our covariates now are going to be gender and idealism or relativism. So what they did in this research is they had the students who were deciding whether the research should continue or not also fill out kind of like a personality scale to see where they fell on the range of idealism and relativism. And so they have scores for that. And then we want to look at the Hosmer-Limshow goodness of fit and our confidence interval. So we're going to check both of those so that we get the chart, and then we're going to get a new model. And you'll note that this likelihood is different than the one we got in the first model because now we've added to it. And so it gives us a different chi-square. We still have a good niggle R-square, but I need to compute my p-value because I've run this twice now with a model, so I can't just use p equals 0.05. I actually have to do something that's called transform and create a target variable. So what I'm going to do is hit transform and compute, and it's going to bring up this dialog box. And when it does, you're going to put a p right here, and then you're going to put this numeric equation, which is basically 1 minus chi-square. And I'm going to pull this information from up here. I think it was up here. No, maybe it's down below. Where did I get that information from? Oh, because our previous model had 3.99.913, and this model has 346.503. So when I look at step 0 and I compare its likelihood with step 1, when I've added in the other variables, then I see there's a decrease of 53.41, which is what my chi-square is. So this is chi-square to looking at 2 degrees of freedom, 1 for each of the predictor variables. So we have the predictor variable of gender, and we have the predictor variable of the type of personality a person has. I calculate all that. It's going to tell us we need a p-value of less than 0.001. So that tells us that chi-square is significant. There's a significant ability to predict using gender, idealism, and relativism when I'm trying to predict accurately who's going to stop the research and who's going to continue the research. Now, I will tell you that I noticed in the class that it really talks about this and, whether or not this is going to be a good fit. But Hosmer-Limshow has even acknowledged that this is not a strong model. So I would take it with a grain of salt and just know, yeah, check it and look at it. But I find more confidence in looking at my chi-square statistic and how that changes from model to model than looking at the Hosmer-Limshow test. So basically, you want this to be high. So if this is not significant, that's a good thing. All right. And with the Box-Tidell test, which is another way that you can do it, you can check to see if your model is linear. That's what I was trying to say. All right, so here we're creating what's called log predictors. So I want to create a numeric expression for idealism. And it walks you through the process of how to do that. So now I have this combination covariant that's looking at, you know, this interaction to see if it is significant. And in this case, it is not. So neither one of the interaction terms, if one was significant, you would try to add it going polynomial, which is a whole nother class. But in this case, this shows us that these alone are doing what they need to do, and there's not an interaction effect. All right. There, he goes on to explain different categorical processes that you can go through to examine a larger model. So in this one, we're looking at these dummy variables. Where was the study about cosmetic? Was the study about theory? Was the study about a meat study? Was it a veterinarian study? Which study was it? And there's actually a fifth one that's represented in the constant. And so in this particular one, we're going back through the same kind of process of looking at our overall test statistic, which is significant. This is going to be good because it's going to be greater than 0.05. We have a 71.7% correct prediction. Remembering that our sensitivity is the percentage of occurrences that were correctly predicted. And then our specificity is the percentage of occurrences correctly predicted would be here. And then the ones of non-occurrences, which were correctly predicted, is here. So this is sensitivity, and this one is specificity. Then you have your false positive and your false negative rates as well. This is the larger formula of looking at creating a prediction, an odds prediction equation. So in this, we can see which ones are significant, cosmetic not so much, meat not so much, veterinarian not so much. So this is explaining how you can interpret each one of those. Talks about how you do it. You can do your classification cutoff. This is all explained. This is from SPSS here, which is what I had to code my dissertation in. And then it takes you to how to write out your results. So this is showing you kind of what the results would look like based on the prediction equation that was created from the logistics. So this is showing you what the support was for allowing the research to continue. This is the description of what we just did and how it was done. And then you have table 2 down here, which gives you the coefficients, your Wald chi-square, the significance, and then the odds ratio. So like with gender, there's going to be a 3.51 increase if you change genders, right? For idealism, every time you get more idealism, it's going to be a change of 0.5. For relativism, 1.39, and so on. And then it goes on to explain interaction effects as well. So I hope that this handout is really super helpful because it does a great job of explaining things. And let me know if you have any questions. I do hope this has been helpful. Talk to you soon.